Okay, so in the last few lectures, last 4 lectures, we have looked at particle motion in one-dimensional systems in various microscopic model systems, and we have seen there are we have looked at some features of particle motion, and we have seen that in some cases, in many cases, there are some common features like the subdiffusive behavior, and in some cases you have similar scaling for the large deviation functions. So the question is, can these results be obtained from some unified theory, some unified formulation? Some unified formulation of these problems, and whenever you try to think of or expect to have a kind of unified theory, or then you try to get rid of various unnecessary microscopic details, and that means you expect to have this theory in large length and time scales, which are basically, in some sense, we'll see that there will be hydrodynamic length and time scales. So you expect to see the system at coarse-grained level, and in the coarse-grained level, you try to describe the dynamics of the system in terms of macroscopic variables, which are density, density fields or current fields. In our case, it will be density fields and current fields. It's sort of similar to the equilibrium statistical mechanics, where you try to describe equilibrium statistical, systems in equilibrium in terms of macroscopic variables. So it will be, but this time we'll have dynamics as well. So we'll try to look at such systems, and it turns out that in many cases the dynamics at coarse-grained level in terms of macroscopic variables are given by hydrodynamic equations, and also there are certain class of systems which satisfy some specific criteria, which I'm not going into the details, but the kinds of models which we have studied in the last 4 classes, they fall into that class, and they are called diffusive class. If the microscopic models satisfy some certain kinds of criteria, then these hydrodynamic equations are like diffusion equations. Okay, so we'll mainly consider those systems which have diffusive hydrodynamics, and that class is called diffusive class. For example, there are microscopic systems which falls in this class is simple exclusion process, symmetric exclusion process, then symmetric random average process, and then the hardcore Brownian particles. Whenever you do not have any bulk drive in these models, you expect to have diffusive behaviors, and so you have this diffusive hydrodynamics, which describes the fluctuating evolution of the coarse-grained densities. Then using that description, you try to extract some information about the tag particle. And interesting fact is that the information about the tag particle is like information of a microscopic quantity. However, you are trying to extract it from macroscopic evolution. So this is possible in one dimension, and I'll show you how. Okay, so let me try to demonstrate the formulation in the context of symmetric exclusion process. So I would like to emphasize that this hydrodynamics, the diffusive hydrodynamics that I am going to show you, it's valid in systems where there are no bulk drive. It's symmetric. Okay, so let me demonstrate this formulation in the context of symmetric exclusion process. So you have this lattice, and you have particles like this. Imagine you have a lot more. sites. And if you look at such a system at a coarse grained level, you can describe these systems by density profiles, right? So microscopically, what would you do? You would represent the state of the system by specifying the occupation variable, occupation status of each sites, which are like tau I variables. Tau I is 1 if it is occupied or occupied, or 0 otherwise. Right? And you specify these variables, and that's how you describe the configuration of the system, and then you try to talk about the evolution of such configuration, evolution of the probability associated to this configuration. But that's the microscopic description. But we do not want to do that. We want to describe the evolution of the systems at a coarse grained level, where this kind of configurations, for each kind of microscopic configuration, you can associate a density profile. Okay? Yeah. And when the particles are moving, this density profile is also changing. And since this is stochastic, so density profile is also evolving stochastically. Okay? So there are rigorous ways. I'll define, but I'm just trying to show you how to get that in not so rigorous way. So let us first look at the average. Suppose I define rho I as tau I t average. Okay. Let us see how does this equation, this quantity evolve. And can anyone tell me how does, what is the equation? Should be the equation for this quantity. Suppose I write down d rho I dt. This is a symmetric exclusion process. So suppose this goes this side with alpha, this side it cannot go alpha. The probability is alpha dt. So okay, so let me try to say. So tau I at t plus dt. So see, in this average, if this variable is 1, then only it will contribute, otherwise it will not contribute. So in what possible ways it can be 1? And it can be 1 if at time t it was not 1, so this is ith variable. So it was empty and some other particle comes from this side and some from this side. These are the two possibilities in which it can be 1 at t plus dt. Or it was already at 1 and it did not move out to this side or that side. That also contributes to this, that it can, in that way it can also be 1 at t plus dt. And all other ways it will be 0. And that will not contribute. If you look at those configurations and then compute, and then you will see that it can be written, the evolution will be rho and this equation you can recognize, right? This equation you have seen in random walk, in Abhishek's class, Sanjib's class. So this equation, we know that this equation has a diffusive behavior, and one can actually see this very easily. Suppose you have this, the system size is L, suppose, then if you try this scaling behavior, suppose I want a solution of this equation in this form, try this scaling behavior in this equation and take L going to infinite limit. This will give you del rho, del, suppose I call this as tau and this as x. Then this will be del tau 1 by L square. That you can see, right? So del d dt will give you 1 over L square d del tau. It's pretty easy to see here. No, this is a random walk, and for a random walk, how does x variable scale with time? It's y square root t. So if you scale I with a L, then you have to scale t with L square. Okay. And if you do that, this will give you a second derivative, and the second derivative will give you alpha L square del 2 rho del x square. And that's how, if you do not take this L square and L, you won't get an L independent scaling, L independent equation for the scaling function, right? So then you can actually take this L square out, and you have that this scaling function actually evolves in this way. So in some sense, this says that at large length and time scales, your average density evolves according to a diffusion equation, where the diffusion constant is alpha, and this alpha is the microscopic information. It was the rate at which the particles are going this side or that side in the microscopic model, right? Okay, so in the later part of the class, we'll always assume that alpha is 1. But for just to show you that how does the microscopic parameter appear, it appears in the diffusion constant. Okay, so you see that these are the continuous variables, the macroscopic variables. I mean, what do I say? The coordinates in macroscopic scales. This is x in macroscopic scale, and this is tau in macroscopic time scales. Okay, and you can see that if you have a small change in your continuous variable, that involves that is like this, right? So the change in corresponding to dx, the number of microscopic points is actually huge, right? It's proportional to L. Similarly, delta t is of the order of L square d tau. So tau you are measuring in your macroscopic scale, macroscopic units. X you are measuring in your macroscopic units, and in that unit, as infinitesimal change corresponds to a huge number of points or change in microscopic units, and that's how you actually coarse grain. Okay. So okay, we see that the average density profile actually evolves diffusively. One can actually define more rigorously the density function, and suppose we define it in this way, that rho x tau is 1 over L sum over I eta I L square t. Oh, sorry, not eta. Suppose I define this function. This is, of course, a density function because these are occupation variables, and I'm looking at this density function at this macroscopic point. I don't know how to say macroscopic point in the macroscopic scale, and in this time, which are scaled. I have made a mistake. This should be tau. Okay. Huh? Oh, actually, the notations are not very good. These tau i's are occupation variables. Let's call them eta. Okay. All of them eta. Okay, and this is the scaled variables. So now there is no confusion, right? So you can define this density function, and of course these quantities are evolving stochastically. So you expect that this quantity will also evolve stochastically. However, in the large L limit, one can show that the evolution of this quantity can be described by an hydrodynamic equation, which is fluctuating. Okay, I'm not going to prove this result. However, for some model systems, these results can be rigorously proved. This equation can be rigorously proved. For example, in exclusion process, and then say in zero range process. Similarly, in random average process, also one can prove this result quite rigorously. And to prove this result, you use the fact that this is the microscopic dynamics is Markov process, and using that fact, actually, you can prove it using the idea, also using the ideas from large deviation theory. Okay, and if you want to see the proof of this kind of results, the derivation of this equation, you can look at this review by L. Bartini and some other authors, Disol, Landin, Jonalazinho. So I'll just write ITLAL, RMP, Review of Modern Physics, 2015. Okay, you can look at this review. Also, you can look at by the same set of authors, JStat Physics, uh, 2002. Okay, this review is, the title of this review is called Macroscopic Fluctuation Theory. So the derivation and analysis of this equation as a different field, which is known as the macroscopic fluctuation theory, and you can see those reviews too for the derivation of this equation. And however, you can see that at least from some simple calculation, you see that at least average has this behavior. But to get this term, you have to do little bit of more work. So now, what is d rho? So this d rho is same as this d. So for yes. Oh, one second. I forgot to change it. It is now eta. Yes. So see, etas are the occupation variable and tau is the scale time. I did not notice that those are same symbol. So just take the etas to be occupation variables, which take +1 and 0, and tau is the scale variable. Okay, tau is the scale time variable. Okay, so now yes. Huh? Okay. Yes, I'm going to tell all these terms. Yes, so, but I'll tell you each of these terms. What are these? Okay, so d rho. It has an index like this. It doesn't have an index. Yeah, if I put xi. Let's say like this. Okay, so d rho is the diffusivity, which is same as this. For exclusion process, it actually does not depend on rho, but for some processes it may actually depend on the density also. Okay, it's called the diffusivity. And sigma rho is called mobility. These two quantities are defined, can also be defined in a different way. So for the time being, consider this following problem. Okay, consider once again, look at the microscopic system. Okay, microscopic exclusion process, and this time suppose you attach it to reservoirs. This side is rho plus delta rho by 2 density, and this is rho minus delta rho by 2. And the particles are doing symmetric exclusion process in between. And they're also coming from the bath and also getting absorbed in the bath. And in this system, if you look at the current, the total number of particles that has, the net number of particles that has come from the left reservoir to the system in time t. In time t, if you look at that quantity, then this quantity, this is the, let me write down the definition, is the total number of, net number of particles transferred from left reservoir to the system in time t. Okay, you can show, so these quantities for diffusive system, for general class of diffusive systems, this quantity behaves as this. For small delta rho, okay, or delta rho equal to 0. Okay, so basically you do this experiment every time with for different overall density, and you do this experiment every time, do this, compute this quantity and take this limit, and you will see that there is a proportionality constant which will also depend on rho if you do this experiments at different rho. And also you can do the same thing where delta rho is equal to 0, and you will see that this quantity will also depend on rho. You do this experiment many times with different rho, and every time with a rho you just put a little, make it little high here and make it little down here. Okay, and whatever these functions, you can do this experimentally and try to find out these functions as a function of rho. These are the functions that appear here, exactly these two functions that appear here. Okay, and you can see that this is basically the current into the system, and current in a diffusive system is basically how does the particle current behave? What is the expression of the particle current in diffusive system? It's d del x rho, Fick's law, right? So this is exactly that expression. It's del x. This derivative is basically del rho by L. Okay, and this is basically the in equilibrium current fluctuations. And you know that these current fluctuations in equilibrium, these fluctuations should be related to this quantity through fluctuation dissipation relation. So these two quantities are related, and they're related via this relation that f prime rho. I'll tell what is f. okay, where F rho is the free energy, is the equilibrium free energy density of the system. Okay, this is like for a particle in harmonic potential, say what-down particle, and you look at that, if you demand that the distribution of the particle, position distribution of the particle should be to the power minus beta half kx square, then the strength of the noise also have to be like 2 gamma kBt, right? It's the same relation, that the strength of the noise has to be related to temperature, and the temperature information is there in the free energy density, right? So what's the free energy for this particle? It's just the energy, which is kBt in some sense. So in that way, this is the relation, and one can actually prove it starting from that relation. If you start from that relation, and so that that in the large time limit, the distribution of the density profile will go to will be something, right? So probability of the density profile, observing a density profile in equilibrium, because the system will reach an equilibrium, will be something. Right? And this I am writing as integral dx f rho, sorry, f rho. This is the free energy density. It will be in this form, okay? Because we know that in equilibrium you have a free energy. You have a free energy means that the probability will be exponential of minus of the free energy in equilibrium theory. Now you can, but you can compute the equilibrium free energy not from just from the equilibrium consideration, right? That in equilibrium, the microscopic configurations will have some probabilities, and from that you can actually compute this free energy. And here also, this dynamics should take your system to that that distribution. And to achieve the same distribution, you need to have some relation between this and this. Otherwise, you will not get the distribution, right? And that's how you can actually prove the relation, this relation. So for exclusion process, what is the free energy density? So let's say for exclusion process in equilibrium, so suppose you have an exclusion process in equilibrium in size L. So the free energy will be energy minus Ts in some sense, right? And there is no energy because they do not have any energy. They're just constrained to move. So you have to compute entropy. And in equilibrium, if you have L sites, and you have n particles. You have L sites here and n particles, and you have to put them. And in equilibrium, the probability of any occurring any configuration is same. That you can also see from the master equation of the microscopic system. You can show that in equilibrium, you can actually see that in equilibrium you can do it for 2 particles, 3 particles, 4 particles in say 10 site systems. You can see that in equilibrium, given a configuration, the number of ways you can go out of this configuration is the same as the number of ways you can come to that configuration. And if that is true, in equilibrium, the detail balance says that if that is true, then the P of equilibrium has to be uniform over all the possible configurations. No, they are moving with some rates, and these rates are given by something which will decide the temperature in some sense. Okay. No, there is not energy involved because they in some sense if they can interact only if For example, in real system, you have interaction potential. And whenever this is the separation, and if these two particle is at separation R, then suppose R is this, then you have this much of an energy, amount of energy. Okay? There is no momentum. It's not an Hamiltonian system. It is kinetic energy. But these are stochastic models where you may not have, for example, overdamped particle. The particle moves, but you do not consider momentum because the momentum has relaxed. In that description, you do not have momentum. But here we are taking that these particles cannot come beyond this. Okay, because these particles can only be in this position of lattice, this position of lattice. Okay, if this particle could have come here, then it would have infinite energy. But these kind of configurations are not there. And since this particle and this particle is here, and the energy is only infinite here, so there is no energy contribution. Okay, so the entropy of the system is basically, since all the configurations are same, so entropy, probability of all configurations are same, it's basically Pi, I don't know, let's put alpha, not put something, some J. J is the jth configuration, log Pj. And these are all same, so same means the possible number of ways you can arrange n particles in L sites, and this will give you log omega, right? And what is omega? Is basically the number of ways you put n particles in L sites. Basically L factorial, n factorial, L minus n factorial. And then you basically take the log and do Starling approximation. You can show that this quantity can be written as n times rho ln rho plus 1 minus rho ln 1 minus rho, where rho is n by L. I think it's L. It's L. This calculation you have done many times, right? So free energy per particle or per length. This divided by 1 over L is basically rho ln rho plus 1 minus rho ln 1 minus rho, where rho is n by L. I am scaling this thing by temperature, or you can assume that the temperature is 1, temperature scale is 1. Okay? Which is same as assuming alpha to be 1. For example, the temperature actually gives you can actually think of in terms of the fluctuations. Fluctuations are measured, the strength of the fluctuations can be, the strength of the fluctuations can be controlled by increasing temperature. So in that sense, you can give a sense of temperature. So, for example, if you have particles and they are moving, and in canonical ensemble, you try to give, in microcanonical ensemble, you try to get a definition of temperature from the fluctuations, and the fluctuation informations are in entropy because there are all possible things. So that's how you can make sense of temperature also. Okay, so since we know what is f of rho for exclusion process, and we know d of rho for exclusion process, at least for one case, for one particular case, we know these two values. So d rho is constant. It doesn't. I'm taking alpha to be 1, so d rho is just 1. And f rho we know, so we can find out sigma rho from this relation, right? And if we put this expression of f rho in this expression, you can show that sigma of rho is 2 rho 1 minus rho. So at least we know one microscopic system in which, if we do a hydrodynamics, we know what is d rho and sigma rho. So there are other models for which there are some few other models for which one can compute d rho and sigma rho, but usually it's hard to compute. You have to compute any from these three quantities. You have to compute any two, and then from this relation you can find out. Now probably this can be computed because we have an equilibrium theory. Equilibrium, you can start from the Gibbs prescription that from this you can try to compute this quantity, okay, which is also a very hard problem, but suppose you can. But it's not easy to compute this also. So here I am talking about only stochastic particle motion systems, but you could think of systems which have actual real Hamiltonians and real interactions, and you can also try to do such a theory. And in some cases, some Hamiltonian systems, you still see diffusive behaviors. You have signatures from microscopic, say from simulations and from some other calculations. And then suppose you want to write down such an equation, then the problem is you do not know what is d rho and sigma rho. So that's the one problem which is still there. And also another thing to note that you see these quantities have all the informations about the microscopic details of the system. Okay, so all the microscopic details go into these two quantities. Okay. Okay, so we have this evolution equation. So let me now come back to our original problem. We wanted to do go to this description to compute some characteristics of tag particle motion for some general class of systems which can be described in this form. Okay. However, so let us formulate that. So xi is a white Gaussian noise. So, oh yes, I forgot to tell you, xi is a white Gaussian noise. So xi would be some noise, and why is it Gaussian? You can actually rigorously prove that it should be Gaussian for some particular model systems. But let me give you a heuristic argument. See, when we are looking at that large length scale and time scales, so this x, so any small element in the macroscopic units dx involves lot of microscopic points. It's like you have all these microscopic points like this. This is your lattice. Okay? And then you are looking at a coarse grain. This is like dx in some sense. Okay? And this time scale in your macroscopic units at which you can dissolve your evolution, in that small time unit difference, there are a lot of microscopic jumps had happened. Okay, so that means in such a small element in macroscopic units, you have lots of microscopic lattice points in which particles have made lots of jumps, and you are trying to, and all these jumps have an accumulated effect into the fluctuations of the density profile. Okay, now when you have all these jumps and you have an accumulated effect of very large number of stochastic variables, such sums are usually, by central limit theorem, behaves as Gaussian. So that's why you can actually try to argue that this will be Gaussian, but you can actually rigorously prove it. And so to see the proof, you can look at this paper or this RMP. Okay. Okay, so we wanted to look at the tag particle motion, which is somewhere. We always think that it starts from 0, and it makes a displacement in, say, capital time T, xt. Okay, but this is a microscopic quantity. However, this particle will also have a stochastic motion because the density around it is also evolving stochastically, right? So that will make the motion of this tag particle will also stochastically. So it looks like that one can try to find out the information about this from the stochastic motion of the density profile. And this is this is possible in one dimension because of the following reason. That, see, since we know that no particle can cross each other, right, in the microscopic configuration, then suppose a tag particle was at 0 and then at time t it has gone xt. This was the origin. So the number of particles which are there on the right of tag particle at time t equal to 0 should be exactly the number of particles on the right of the tag particle even at time t, because no particle has crossed each other. So by doing this from the particle conservation, you can see that x of t to infinity, what is the number of particle at time t? Suppose this is the configuration at time t. So this is the number of particle on the right of tag particle at time t. This should be exactly equal to the number of particles at time 0. Right? So that gives you, given rho, you can in principle from this expression find out what is the position of the tag particle. Okay? Now this quantity is, this relation establishes the fact that this quantity is a functional of, in some sense it's rho xt, but you can see from this relation that it actually functional of one rho of x at capital T and rho of x at 0, only at the two final times, right? So this establishes a functional dependence of the position of the tag particle on the density field. So the problem boils down to this, that we have a, no, there is no half factor. Why should there be a half factor? This is not the total particle. Total particle is minus infinity to infinity. This is also the half of the particle, in some sense, if in your language. This is the number of particles here, and since this particle has moved here, so all the particles has moved there. That's the relation. So the problem boils down to this, that we have a fluctuating density field, which is fluctuating according to this expression. We have a functional of this fluctuating field, and given the statistics of this, we want to find out the statistics of x of t. That's the problem. The formulation in quantitative formulation of the problem is that. Okay, and that one can do in some way, but instead of, okay, so let me go in with the formulation a little bit more, and then we'll do something. So to compute properties of xt, it is usually easier to compute, or convenient to compute the cumulant compute the characteristic function of x of t. Okay, let's call it z t lambda. Okay, it's usually convenient because if we know this, and then the log of zt is the cumulant generating function. By taking derivatives of log of zt with respect to lambda, you get moments, cumulants of x of t. The question is, how do we compute zt lambda? So it's basically, this average is the average over this stochastic evolution of the noise, of the density field. And the density field is having stochastic evolution because of this noise field. So I can write down this an average over noise field, but this average over noise field cannot be arbitrary. We should always satisfy this equation. This equation we should always satisfy, right? So we sum over all possible configurations of the let me first write down the expression. This represents you are summing over all possible density profiles from 0 time to capital T time. Okay, and then you and only those configurations will contribute in this which satisfy this relation. And then you average over all possible configurations of zeta with their respective probabilities. And these are white Gaussian noise, we know what are the probabilities. And this is a functional delta function. You can think of in some sense that, so delta function of a variable is x minus y. If you have delta function of two variables, you put delta x1, x2, y2, and you can keep on doing that. And you can think of these indices are like continuous in this case, from 0 to capital T. Okay, and that way you can make sense of this delta function. So basically we have to do that. So by doing this average, we can find out zt lambda, and suppose mu t lambda is log of zt lambda, then this has an expansion lambda xt, then lambda square by 2 factorial xt square cumulant lambda cube by 3 factorial xt cube, and that. So if we know the lambda dependence of this, then we can have try to get an expansion in lambda of this quantity, and from the coefficients we can read off this. Not only that, if you know what is mu t lambda, so this means actually, yeah. So from this zt lambda is basically e to the power mu t lambda, right? And then to get the distribution of xt, you have to do an inverse transformation. And while doing the inverse transformation, you can actually perform some saddle point calculations, as I was telling yesterday. And then that also has the information about the last deviation function of xt. Okay, so I'm not going into that. Before that, let us try to see how how to go from this to this, how to actually compute this right hand side. So to demonstrate that, let me consider a simpler problem, a much simpler problem, which is not in terms of fields, but in terms of a single variable. So this means that this says that there exists functional, that xt is a functional of rho of xt. So when you do this calculation, you will see that it can be written as an path integral with an action, effective action. And when you minimize or extremize that action, you have to take that into account. And that, the functional derivatives of that will be computed using this. Okay? Okay, so let me demonstrate how to do this calculation for a single variable which has time dependence, not for fields. Fields is basically infinite number of degrees of freedom. Let's do it for single degree of freedom, and let me demonstrate this. I have only 30 minutes. So let us consider this problem, that x dot, don't confuse with x and this x. This is just a simple Ornstein-Uhlenbeck process. Ornstein-Uhlenbeck process. Okay, which is x dot, x is the position of some, the velocity of some particle, and it has damping. Sorry. Plus a noise. This is why it causes noise. This is the Ornstein-Uhlenbeck process, all of you know, right? And I want to compute, say, different kinds of quantity, say xt average, xt prime average. These are much more detailed question than this. But suppose I want to compute this kind of things, and I was to use similar formalism. How do I do that? So for this thing, once again, similarly, I'll consider a functional which is integral lambda t xt dt, is 0 to t. Here I am taking a functional which is also a time-dependent function, but this will be same as this if you just take lambda t to be lambda times delta of t minus t. This will become same. So let me demonstrate it in this case, because in this case you actually can demonstrate easily the full problem. Okay, so this is, how do I find out? So once again I'll write the same thing. I'll write a path integral of these trajectories, okay, of e to the power 0 to t dt lambda t xt, and with a condition, delta function condition, that this has to satisfy and once again this delta function is at every instant of time. Okay, this is same as this, only thing is that you have an extra index rho of x of t, right? X is another index we have, but we do not have such, it's just one variable, one degree of freedom. Okay. No, lambda t, I'm trying to compute this, average of this. Huh? I'm trying to compute this function, average of this function for given lambda t, lambda of t. I'm saying this problem will map to that problem exactly when you have lambda t is lambda times delta of t minus t, that is exactly that. That's what I'm trying to say. But here you can do it, so let's do it, a more general problem. Yeah, you are averaging over noise configurations, summing over all possible x trajectories you can think of, but only those will select because of this delta function, which satisfy this equation. No, x is rho here. That x is not this x. Let me put it y. Probably y is good variable. Let me make it y. It's the Ornstein-Uhlenbeck process, and it's the velocity of the Ornstein-Uhlenbeck particle, right? Now, suppose you have many such particles, say y1, y2, y3, y4, and then construct a configuration of y1, y2, y3, yn, and then say I want to describe this by a density, okay, of these y's. Then you have another index of y and t, and that's how you get there. So in that way, but this is just one particle, and is it clear? The rho is basically you have many such trajectories of all particles which are has infinite number of degrees of freedom. Rho has infinite number of degrees of freedom in some sense. Okay, so this delta function I want to replace. Suppose you have a delta function like this, you can replace it by 1 by 2 pi dk to the power I k z, right, for one variable. So you can do it for each time, and this can be represented by introducing, say, let's y, and let's define another auxiliary field which can be written as right? And all the constants, whatever is there, let's put it in some normalization constant here. Whatever the constants it may appear. Okay, there may, I just put it in this form, in this n, and we'll fix this normalization later. So this you can do. Now this average means what? This average of with respect to zeta means you have a path integral with respect to xi, and the probability of xi, which is also proportional to e to the power minus 1 by 4d integral xi square t dt, right? This average right? So we will do that average in this form. And since this do not depend explicitly on xi, only this times this depends. So this is basically n times d of y hat, and then e power 0 to t dt lambda t yt, e power minus I 0 to t dt y hat, and then you have e power minus I 0 to t dt y hat xi, average over xi, right? Now this is a Fourier transform of a Gaussian in some sense, and that you can compute. It's basically Fourier transform it's basically multiple Gaussian problem, and that you have done it many times. I'll just write down the answer. The answer is the following. Oh, I erased. Okay, so this term I want to write, and this term, all of you have written this term. Okay, Otherwise, again have to write. Okay, let me write it. So this term is e power minus d0 to t dt y hat t whole square. It's for Gaussian integrals. So let me replace now this term here. Okay, and now I can erase this term. Okay, let me erase these earlier lines. You can see that this thing can be written as in dy dy hat. Let me write it in this form, shorthand notation. E power minus s of t y and y hat. S is some action, right? Where s okay. I just rewrote this term. I just summed of all the and have taken a minus sign out, so like that. It's clear? No, you had this delta function. I removed the delta function by introducing this dk e to the power I k z, right? And by removing that, I could have made the zeta dependence kind of product. So instead of putting this delta function condition, I have introduced another variable, another field, and then integrated out the zeta variables. That's the usual trick you do when you have delta functions inside this thing, right? So instead of these zeta variables, now I have an y hat variable. Earlier it was sum over x paths and zeta paths, which were constrained by delta functions. I have removed it by putting another auxiliary variable path, or say, I don't know how to say, function, y and y hat. Okay, so now next step what I do, I'll try to extremize this action and say write this thing as e to the power minus st of q and p, where qp are the optimal paths which extremize this action. It's now similar to the what you do in quantum mechanics, the path integral, right? And whatever other things you can put it in the normalizations. And you see that when you, what do you find out, how do you find out the optimal paths? You do this, the functional variation. Write down delta s, which is s, and suppose the q are the optimal, q and p are the optimal paths, you do a variation around these optimal paths, right? And find out the deviation from the optimal paths and make that equal to 0. And this you can write, usually you have something into delta q and something into delta P. That we have done this kind of extremize in classical mechanics many times in quantum mechanics. So I'm not repeating this. And then since this has to be, these are basically functional derivatives. That's how you compute functional derivatives, right? So this term is the functional derivative with respect to Q variation. This term is the functional derivative with respect to P variables. So this has to be 0 means this has to be this, all these derivatives have to be 0. And that gives you the Euler Lagrange equations. So here we'll get the equations for Q and P, and the equations for Q and P are, I'm just writing it, optimal equations. You can, this is very easy calculation, you can do it, I'm pretty sure. Yes. That's what you do usually in actually for this particular example, this is exactly that. This is exact. Even the saddle point is exact because it's a quadratic action. But for other cases also it will be quadratic because of the. If d rho and sigma rho are not rho dependent, but if they are not, they are dependent, then it's not. And there you have to do saddle point calculation, but you'll see that it will be enough because this action will be quite extensive. It will grow as the square root t. Okay, and this is equal to minus lambda t. You see that lambda t appears into the equations for the optimal paths. So the solutions of the optimal paths actually depends on lambda. And you put it here, so these functions actually depends on lambda, right? In some sense. So this is actually the in this form. It's actually in this form. So you know the cumulative generating function of y of t because of this. You know that. And once you know that, by expanding this in lambdas, you get all the cumulants of y. Okay? So, and another thing to note that here I have taken the delta function, delta of z to be dy hat e to the power I y hat z, like that. And I had taken this I is actually is always with the corresponding y hat field. So I could have written, instead of writing I can do this calculation without this, taking the absorbing the I into the definition of P itself or Y itself. Yes, but this is a Gaussian integral. This is quadratic. So here it's exact, but there it will be. It may not, for example, in many cases, it may not be that it is explicitly something is large quantities is coming out and explicitly present. You can make it explicit, but those quantities are extensive. So since those quantities are extensive, and you are summing over extensive number, exponential of extensive numbers, and the largest contribution will be the largest number. That's the simple idea, and you are trying to find the largest number. Okay, so by solving these equations, you know what is this. So I'll just write down the solution. It's the solution of this equation. Okay, and one more thing I forgot to mention. While doing these things, you'll also, by doing this, you also get the initial conditions. When you do that for Euler Lagrange equations, and you'll get P of t equal to 0, and the initial condition for Q variables are that you start from some position. So Q of 0 is Q0. Okay? Q of 0 is given, and this you choose. When you do Euler Lagrange equations, you have to, because there are some derivatives and you do partial derivatives, and then they will be at the boundaries, and you have to make them 0 also, and by that you get those conditions, right? So you'll get this, and these are single time derivatives, so one condition for each of them is enough. So you solve P equations with this boundary condition. with this initial conditions, and the solution is given by this. Okay. So use this solution into the expression of the action and also the solution from the other equation, but you will see that you don't need to find out the solution of this equation because the action already has an expression like this, which is exactly the left hand side of this equation. So I want to evaluate A's of Q and P. Put Q and P into this expression, simplify, you'll see that you'll get a d0 to t dt p square minus q naught 0 to t ds e to the power minus alpha s lambda s. Okay, this lambda s is the same function which is appearing here and there. Okay, and p has this expression which also depends on lambda. Let me put a lambda there so that it reminds us that this also depends on lambda. Okay, and you see that p is linear in lambda, so p square is quadratic in lambda. It will be some quadratic functions. So this is our, since we wrote in this form, this is our exactly the cumulative generating function of this stochastic trajectory. And suppose I want to find out what is y average t. I will do the functional derivative of this s with respect to delta at lambda t, and then take lambda goes to 0, right? That's what we will do. And since this is quadratic, this term will not contribute, and this term will contribute. That was minus s, I think. Yeah, it was minus s. Okay, and if you do that, and you'll see that this will give you q naught 0 to t dt e to the power minus alpha s, sorry, e to the power minus alpha t theta of t minus t. This theta comes because we are probing these things only over 0 to capital T. And you could have taken capital T to infinity, then this theta function doesn't matter, right? And this is exactly the average why you would have, because this equation can be solved exactly, right? You can write down the solution of this equation. The solution of this equation is yt is y0, y at 0, which is q0, e to the power minus alpha t plus 0 to t dt ds e to the power minus alpha t minus s xi s. Right? This is the solution of this equation. And you can see that the average of y is exactly this. Right? And that's what you get. And similarly, you can compute yt and yt prime average from this. And there also you can compute just by taking the derivative twice. Actually, not just this, you have to subtract the mean. So let me put cumulant. If you take derivative twice, you will get so this function is basically written in this form: 0 to t, 0 to t, and then something lambda t1, lambda t2, right? because P is in this form, not 0 to T, T to T. Right? This will be in this form because P square I am writing as the multiple of two integrals here. And if you take the derivatives with respect to two lambdas, functional derivatives, you will get this expression, which you will probably all have seen. 2D e power minus alpha t minus t prime e power minus alpha t plus t prime. That expression you have seen in Von-Steulenberg process. You can that also you can do it from here. You can do this. It's basically cumulant means y minus, this can be written as y delta y t prime. Delta y is y minus the average of y at time t, and that will give you that and then you put this, and then you have zeta s1, zeta s1, zeta s2, and use this and do this integral, you'll get exactly that answer. Okay, so this is a kind of very difficult way for solving, at least for just for this problem. You can get all these results just by solving the direct equation, but that is not possible there. The problem I had for this problem, it's not possible. So, but you can do this method exactly and write down this thing will be e power minus st of, say, now density profiles, optimal density profile and the corresponding conjugate optimal density profiles. And these profiles will have again some Euler-Lagrange equations. And let me write down those equations. Can I write it as capital Q, capital P? These are optimal fields. This is for rho, and this will be for rho hat. Because when you replace this delta function, you have to introduce another conjugate field which is similar like y hat. Let's call it rho hat, and the optimal for the rho hat is P. So the equations are del T Q, del X dq, del X Q minus del X sigma Q del X P sigma prime Q means the d sigma Q dq. Okay, just that. So these are the equations, and you'll get some corresponding boundary conditions. Let me write down the boundary conditions. So suppose you start from this initial configurations where the particles are from fixed positions, which we had introduced earlier. It's called coincident initial configuration. That means that particle starts from given initial density profile, and usually we start from constant density profile. So let's say rho naught, and from the saddle point calculation, when you do the extremization of the action, you will get another condition, which is P of xt equal to lambda by Q of y Q the density evaluated at the position of the tag particle. And suppose I just write for notational convenience that xt at time t is as y. You can write it as xt also. Okay, so you have to solve these equations with these boundary conditions, and once you have that, you put those solutions, and of course these solutions will depend on lambda, right? So they will depend on lambda. So you get an expression in terms of lambda, you expand, and you get all the cumulants of xt. Okay, that's the procedure. So I do not have time to show you the procedure, how do you do it for general D and sigma rho. For general D and sigma rho, since we know we want this function as an expansion of lambda, so we can try to solve these equations in orders of lambda at different orders, and just by improving the solution at different orders of lambda, you can get different orders of the expansion terms of this. And just by doing that, you can, so for example, if you want to know Q, if you want to know Q of lambda xt, suppose this has, so at order lambda equal to 0, at order lambda power 0, you should have this our initial density profile, then you have fluctuations, then and similarly P will also have, and this doesn't have any order because it's already proportional to this, so no lambda power 0 term, so lambda P1 plus lambda to P2 like this. You can try with this kind of solutions and put them and equate equations for both sides of each powers of lambda, and you'll get hierarchy of equations. And once you know the solutions of the previous order, you can use that in the next order, and that's how you can keep on going it. And then you know rho naught, and from rho naught you can find out Q1 and P1. From Q1 and P1 and rho naught you find out Q2, P2, like that. And then that's how you can improve these solutions, that if each order of lambda, put it here, and that will automatically give you an expansion of S in powers of lambda, and that's what we want to find out the cumulants of x of t. So if you want, I can explain that procedure or show you in the tutorial class how to do that calculation. Okay, so I wanted to make some comments that this is kind of a general method by which you can try to find out the various moments of cumulants of tag particle displacement. However, the difficult part, as I also have mentioned, to find for a given microscopic system to find out what is d rho and sigma rho. This is one of the difficult part. Second is, suppose we are interested in the last division function, because usually people, ideally one is interested in the distribution of the xt. Not only few moments of the full distribution. And to find out the full distribution, you need to solve these equations for all orders of lambda. Okay, so you have to solve these equations completely with these boundary conditions, with these conditions. With these conditions, you have to solve these equations. But solving that for arbitrary dq and sigma q is difficult. There is only one case where it has been solved, which is the Brownian case. So for Brownian particles, d rho is again constant. D does not depend on rho, it's just constant 1. And sigma rho is 2 d rho. D is constant, so just 2 rho. That also you can show it from just by computing the free energy density, and then you can show that it will be this. So only for that case, these equations have been solved exactly. And once you know these equations, then you know this expression for all orders of lambda. Once you know for all orders of lambda, then you can try to find out the large deviation function just by doing saddle point calculation. And saddle point calculation means that you have to take a Legendre transformation of this function with respect to the lambda field, lambda variable, right? That's what always happens when you do large deviation function calculations. In the saddle point calculations. Saddle point calculations effectively are Legendre transformations of that action. Okay, so this is a second comment, and the third comment I wanted to say is that in this till in the full set of lectures we have talked about only stochastic models, and we have considered only very limited interactions, which are like hardcore interactions. But the question is, can one also construct a hydrodynamic theory for more general interactions? And there is one in some way for Langevin particles, where these Langevin particles are interacting by general interactions. You can actually construct a hydrodynamic theory, but you don't know, nobody knows how to solve them for general interactions. And I think in the next week there will be a speaker who will talk about that. Probably. Huh? Maybe you will talk about that how to get hydrodynamics for particles which are moving according to Langevin equations but interacting via general interaction potentials. This is the third thing, and the last thing I wanted to say was the last thing. And also, one can try to do similar calculations for situations in which the tag particle itself, just the tag particle, is driven. All other particles are doing symmetric motion, but just the tag particle is driven. Such problems are important because in many cases, for example, in active microradiology, you actually pull a particle inside colloidal solutions. You confine the tag particle in an optical tweezer, and then you move the optical tweezer. So you actually basically pull that particle. So you put external force on that particle. On the other, whereas the colloidal particles are doing whatever they want to do. So such problems are also important. So the simplified version would be a simple tag particle which is driven in one dimension in these models, and try to see. So the performing microscopic calculations in those models are very hard, and also, but however, one can do some hydrodynamic calculations in those cases. And yeah, that's all I think. Thank you. Oh, so I have erased 1, 2. Okay, so that you have noted down earlier. Yeah. No, those are for the derivations of the hydrodynamic equation. This kind of calculation, the procedure for this, I'll tell you. This is, I should write somewhere. Let me write it here. Krapivsky leak page, this is volume, page 885 and 2015. This is a kind of short review on this, where you have this calculation. But this calculation, I think it's not there. It just, you can do it analogous. But if you read that and try to do it, you can do it.
You are getting all the moments of xt, right? That means like yeah, all the information about the distribution is still there.
Yes, all the moments means you have to, in principle, you know the solutions of all orders. But very quickly the equations and will be so complicated that you will not be able to solve, which will be as difficult as solving the full equation.
Even I'm not considering about solving itself, because after considering the extremum case, you are getting these differential equations. From these differential equations, ideally you can get all the moments of the distribution.
Yes, ideally, in principle, but to get explicit expressions, you have to solve these equations.
But it should not be possible, right? Because like, yeah, it's an approximation, right? Like
no, I have neglected in the saddle point approximation. When you do the saddle point approximation, actually this S, the action, you can show that this will be proportional to, for say exclusion process, will be root T. So root T, there is a big term. T is large. There is a large term. And this is giving you the probability. This will give you probability of xt in this form. It's in the large deviation form, which means that the p of xt is log of p of xt by root t. If you take large t limit, it will converge to this function. So that means it will give you the cumulants at leading order in time.
This is for the large deviation distribution only, right?
Yeah, so this will give you all the moments at large t. So you will get all the leading term of all the cumulants at large t. You will not get the next order terms, but the leading terms.
If I write the distribution of p of xt for any time, like, are these moments same as the moments that you were talking about?
If you know the full distribution, you compute it, then take the large t limit, the dominant term will come from this, exactly that.
But the moments are due to the entire distribution, right? So
yes, but there could be other terms which you cannot get it from there. Is it clear? You have the full distribution, you compute it, and that will have the exact expression. But in the large t limit, you can also expand that exact expression. The dominant term, whatever the dominant term is, you can get it from this.
So all these moments are only true for large t?
Yes, this is a large t behavior. This full thing is large t behavior because that's the point of using the hydrodynamic description. Otherwise, you could not. If you want to do it, suppose you start this motion and after say 10 per minus 5 seconds, you want to ask the fluctuation. This thing will not be able to give you that information. So, and in the full lectures, set of lectures, I have always considered the large t behaviors, because those are the things interesting and also you can actually try to understand. For small t behaviors and other things, in some cases you can understand. The intermediate t's are extremely difficult and to understand.
Okay, any other questions? Okay, so that was a great set of lectures. So this was the last lecture. It was, I guess, tough, but it was really good. And he also introduced large deviation theory, which is a very important current area. And I think in the next week also we'll hear probably some related lectures on this hydrodynamics. So let's thank Anupam for his lectures.